I'm gonna probably section these off into 1 hour bits only because sessions normally go 1 hour, and that's probably where the attention span can fall off. But in the live streams, you'll be able to see all of the actual um, pieces separated into their own sections. So it would be part one, part two, and so on and so forth. Let me see. Set up real quick. All right, so welcome to the office hours. Continued part two. Continuing on from last moments ago. Just took a quick break, got some coffee, rejuvenation, and continuing on. Um, where to go next? Well, we got plenty of students to go over. So let's check on Joe. Sequence geometrics. Yep. Sequences, they're pattern finding. Yeah, that's basically what it is. Um, Hard to really go over at this point since we're kind of working with a really basic stuff. So I'm not going to go over this explicit and implicit factors. But it does raise a point where Joe had some issues with exponents. So here's a little bit of a look-see into that. And again, even if you're going to advanced math, you're going to have issues with smaller bits and pieces that pop up because maybe they weren't understood in the past. They were not explained well, or bad teacher, most case scenarios, or just going so fast that thorough investigation of a specific subject like exponents wasn't made. So let's do that thorough investigation. And that has to do with PEMDAS still. The last two that we haven't talked about yet. These two also relate a little bit further down in the algebra space, but we can relate exponents at least to multiplication. In the case that we have 4 times, let's do it straightforward here. 4 plus 4 plus 4 plus 4. The relationship between addition as a cousin relationship to multiplication, again, is just a shortcut. We don't like how these particular values are written over and over and over again. It's a copy and paste situation. So in multiplication, we simply do 4 times 4. This would be 16, and this is also 16. So nothing really changes there. Then, in another copy and paste scenario, give me a second. Having issues joining the stream so I can keep track of chat. There we go. In another case scenario, exponents are basically just another way for us to be lazy, extra lazy. And if we see copies in multiplication, we just convert that to 4 to the power of 2. Or if we have 2 4s multiplying. So addition, interestingly enough, has a relationship with multiplication, which then has another relationship with exponents. And in the base case scenario, they basically just reduce copy and paste, reduce rewriting. Um, and this is where it really starts to play a key to some factors that are involved in exponents. Let's see, Joe again, what was his issue? Yeah, okay, it was based on the factor of negatives. So there's two ways we can show the sort of exponential progress. We have a parenthesis around the things that are being exponentiated to. In this case, just a positive 2 being a 4. But there's a big difference between a positive 2 squared to a negative 2, and the fact that not of the outcome, because they're both going to be a positive 4 in the end. But it really depends on if a negative 4 or a positive negative 2 or positive 2 is being shown the exponent, the parenthesis. I'm going to make these backwards issues here and there. So in this case, the priority is not a negative because in PEMDAS, the subtraction is the very end. The focus is the exponent. So because the exponent doesn't necessarily state a parenthesis, we always assume that the 2 is being squared, not the negative in the front. We would have to explicitly put a parenthesis and show you the parenthesis is around that -2 in order for us to say, okay, now you can put the minus with the square or the negative with the square. So this is why you'll see cases where you have two of the same looking things, but this one's going to end up being a positive 4, but this one ends up being a negative 2 times 2 or a negative 4. Because in the second option, we didn't actually confine the negative in our exponent. And the first option, we have explicitly put a parenthesis there so that we can essentially now consider that a part of the problem. And more the case of the PEMDAS case. Parentheses in PEMDAS comes first versus the exponent in PEMDAS and the subtraction in PEMDAS. Exponent comes first, so we don't include the minus on the second case. But parenthesis already is the first thing we focus on, so we group them together and then do a -2 times a -2. Another common issue with algebra. We're not seeing, or at least not registering, this sort of factor, the pieces that make up our operation. And this can also happen, even if you understand it, it can also happen just through rushing. A test that's an hour, you don't think of every single possible case that you'll catch yourself making a mistake like this. So a very common mistake here is that we let go of the fact that a parenthesis has to exist for us to actually include the subtraction or the negative involved. Oh, what else was? What else was? Fractions, a little bit of an issue here and there. Oh no, we're just finding patterns. Geometry. This one was fun. Did you know? If you have a single number, we consider that by default a length. In fact, it's not arrows, it's a specific beginning and end. So, like a measurement on a ruler. When we multiply another number to this, in our case a 3, we're actually changing dimensions. We're not just multiplying here. We're actually changing dimensions. We're going from a single linear dimension to a two-dimensional figure. And we can kind of draw this out as a rectangular prism. Not prism, just a rectangle. The prism comes in the next step, where we can multiply another value. And this is kind of like the step where we're now in 3 dimension. This is where it stops, because multiplying further won't necessarily bear us any extra dimensions that we can identify. But this would be more the third dimensional stretch, where we can now consider this to be a rectangle, or a rectangular. There was a specific name for it. Forget the name. Again, vocabulary not necessary as long as you understand the logic. Something piptoid or rectangular piptoid. I can't remember. But there's an interesting case here where multiplying actually changes dimensions. That's something a bit in the world of today when we're playing all these video games and going from dimension to dimension and beating enemies and stuff. It's like, wait a minute, I'm just multiplying into a new dimension, basically. So anything basically works this way, even to the most difficult looking things. In fact, if we take a look at this space, if we really focus in on the 5 times 3 representing this face, this area, we're taking that area and then stretching it backwards by 2. One here and another section here. And we create volume. So the multiplication not only shows us like the area of one spot, but now we kind of expand it into the back and create a three-dimensional figure. This works also with more complicated shapes. The one is like a cylinder. We got to kind of find a basis of stretching in the third dimension. So we can't really look at the face, this part here, because it's kind of round. But we can take the circular top. Remember that pi r squared is that area at the top, the whole area. Let me get a highlighter here. And what if we wanted to essentially find the rest of that third dimensional space? Well, we just multiply it by where that space is stretching. And it's stretching on an up and down movement, our h, our height. So the area for the top of that cylinder is pi r squared because it's a basic circle. And then we stretch it down to create that third dimensional movement or that cup that you can put water in now. So that was one of those. Square roots. Those are fun. We don't necessarily think of the radical as anything other than like a fancy looking, not so Nike symbol. But when we dive much further into it, any number inside of that radical is basically going to translate to an exponent. Radicals are exponents, they're just fractions in the exponent. So this would actually be 1 over 2 off the bat. Nothing crazy there. We don't have to write the radical. We can just put a fraction in the exponent and we're mimicking that radical. And the reason for this is because this was a square root, so our 2 is essentially the focus of the index. So that index ends up being at the bottom of a fraction, and there's always a 1 on top. There's a 1 everywhere. There's an instinct to this too, a mathematical instinct to what is around a number if we don't necessarily see it. Now, we can basically translate every single type of radical to the fifth, which will be just 1 over 5. There's a specific reasoning behind how we can use this, but in the most case scenario, you'll just take a 4, realize that's 2 squared, and then you got a weird 1/2 up here. Now we're kind of changing the way the 4 looks to a 2 squared because it is a definition of it. It is 2 times 2 or 2 squared. And then the radical sticks around, which then, well, one of the properties is if we have this sort of exponentception, an exponent to an exponent to an exponent, to bring it down, we just multiply those exponents. So this would be 2, and then 2 to the times 1/2, which basically makes 2 over 2. And based on division, that just becomes 1. Hence, when we actually finalize this, square root of 4 is 2. Because the logical concept is, hey, I have a 4. What two numbers that multiply together make 4 that are exactly the same? That's how we normally solve these. It's 2. 2 times 2. But we don't think about the fact that, hey, there is an actual reasoning behind what a radical is because we're just kind of taught to say, hey, here's a nice square root, 64. What two numbers multiply to give you 64? We think. Well, 8 and 8. But that's also 8 squared. So because this sort of interaction with radicals and exponents, we can mathematically, clear out that exponent with a 1, or we can just deduce that logic of, hey, what two numbers give you a multiplication, or the same number twice to give you 4. This also opens up the way to simplify radicals, so that's a case to consider too. Yes, indeed. Oh, actually, let's check this out. I give you a number, any number in mid-space. There's invisible things around it since we have some viewers. What do you think is around 5 that we don't normally think about? Something that's around the number 5. You can use any operation to show it, but it's technically there but it doesn't affect 5. It keeps it still the number 5. I'll give you the first hint. There's a couple of them. The first hint is there's a 1 in the front, multiplying. Anything else? Any ideas? What about underneath it? Anyone know what might be underneath the 5? Well, it's also a 1. Big surprise. That's how we change things to fractions whenever we need to. We don't think about them. We don't think of them as being there. We don't even consider, yes, and there we go. And there's an exponent. So these are what I call mathematical or math instincts. Just like we breathe without thinking about it, we eat when we're hungry, normally, instincts. There are these values that exist around this 1 or this 5 that we can pull out anytime we want. And this is what teachers do sometimes. And when you go through space and space and space, like a rewrite there and a rewrite there, sometimes things start to miss. You don't know where something went. Maybe sometimes some number pops up out of nowhere, like the next case. What about a plus? What can I add to 5 to keep it the same? You have infinite numbers to try. What number added to 5 keeps it exactly the same? Because we know multiplying of 1, dividing by 1, and the exponent of 1 all have or all keep 5 the same. But now we're thinking addition. Something that can be added to 5 might be a 0. Yep, there you go. You got it on spot because I was writing it. So here's the trick. A 0 is not just a 0, is it? Because what can anything become a 0 as? Or what can any operation combine to be a 0? Well, let's say plus 2 and minus 2. Oh, now we've got ourselves a problem being made. Pops up out of nowhere. This is where numbers tend to pop up out of. When we understand that there's these invisible pieces around, teachers tend to pull them out, show you a number, and then you're like, where did that number come from? Where it probably came from a situation like this, where you have a number like 0 that just splits into two numbers that are opposite. This is not crazy like magic. You understand it when you see it, but you don't think about it, and that's why it's an instinct. Well, I didn't talk about the 1 in the front, but isn't that also technically 1 over 1? Yeah, it is. What about 5 over 5? Totally true, right? So we tend to continuously do this, and hey, let's make a problem for our students. I want the answer to be 5, but I don't know what to do. I'm not creative enough to think of a problem, so I'm just gonna start making random stuff up. So now I can do 25, multiply the 5 in tops, right, over 1, because the invisible 1's at the bottom. Then we have 25 over 5. You add the 2 minus 2. And instead of putting those 2's together to a 0, we're going to put this over a 1. Multiply the top by 5, bottom by 5. We got 10 over 5. Add it with the 25 over 5. And that'll be 35 over 5 minus 2. And here's a problem for one of my students. Solve this. I know it's a 5 because I started from the actual answer. And I just started modifying it. Now I have an actual problem I can present. I can move any numbers around and start playing around and basically give different problems based on my final answer wanting to be 5, just by pulling out these instinctive factors. So the math instincts, I wouldn't say every teacher does this, especially not with computers and all this stuff that can generate stuff for you. Maybe the computer does this, but even AI, we don't understand how it works exactly. But it all starts from these mathematical instincts. There's a 1 in the front multiplied by 5. There's a 1 on top, 1 underneath, plus 0. Now I can just remove 5 and put an x here, and x represents every single number we can possibly think of. Try writing every single number and all the instinctive factors that we think about. You're going to be basically writing forever. So this is something that you don't do on paper. This is something you keep in mind when you're actually doing math. And whenever you need something like I have 5 minus 2 over 3, you think, well, how do I add fractions together? Oh yeah, every single number has a over 1. So let's make that happen. So we open up 5 divided by 1. Now we can start working with the next step. Well, I need this 5 and over 1 to match the denominator of the 3. So what do? I take a 1 in the front. Here's not the shortcut. This is like the straight up process we do. I take the 1, I change it to a 3 over 3, and then I multiply it with the 5 over 1. This is why we say when you multiply the top, you multiply the bottom. Why do we do that? Because we're taking a number out of nowhere. Not nowhere, it exists there as an instinct. And then we change that 1 times 5 to a 3 over 3 times 5, and then we combine them. 15 over 3 minus 2 over 3. And now we have the basis for fractional subtraction. The denominators are the same. We combine them on the tops. Don't change the bottom. Yep, I did that right. And there's your final. So these instincts come into play so much, but we don't show them every single time we do them, which is understandable. There's no reason to constantly write a 1 and then change that to a 3 over 3 and then proceed to mix it in with the 5 over 1. But you'd imagine this would be at least the first case scenario for any teacher introducing fractions. But then you'd have to assume somebody specified all the details of our instincts. That there is a 1 in the front, 1 times the number x. That there's also a 1 at the bottom. And then there's also 1 in the power, which is where we finalized our radical. This 1 that happens to happen when we take a square and a radical, we change the radical to look like a fraction in the exponent, and then we combine those two, whole number 2 and the fraction, and boom, there's your 1. And then this would be the answer in the mathematical sense, where if you wanted to prove it, because in math eventually you go into proving your steps, you would prove it this way, but you would solve for problem this way, because you don't have to show every single step every time. Cool. Well, that's kind of the pieces here for that one. What else do we got? Oh, I hate them. Mixed fractions. We never use these. We use them only when we're dealing with like length, meters, inches, kilograms, weight, all kinds of stuff like that. So we can visualize it better. So like a fraction that's 23 over 4, um, let's say inches, or whatever unit you want to put into it. It just makes more sense when you're using units when you're doing mixed numbers, because then we can say, okay, it's at least 5 inches, even though the 3/4 is a little bit like, okay, cool. But when we use mixed fractions, generally speaking, I personally don't like them. Um, they're not of my favorite types. In fact, the shortcut that we do in mixed fractions is basically the same thing we've been doing before. They just have a specific format to keep these two as close as possible, but in relation, this is just a straight representation of 5 plus 3/4 without actually saying the plus, which makes me roll my eyes because at this point you're confusing the poor students. They're trying to understand fractions, and now you put in mixed fractions, and you're like, all right, well, yeah, you can put them right next to each other. It's called a mixed fraction, but it processes the same way as it would if it was just an addition of fractions. Because what do? We multiply 4 into 5. We get that 20. Well, that's the same as basically doing this. And there's your 20. We don't show that fraction. We don't show the interaction that happens, but we're doing it as a shortcut. So that's why I hate shortcuts. Shortcuts hide the, or obfuscate and hide, really, same word, the actual meaning of what we're doing. It's great to do to save time. Don't get me wrong. I'm not going to do this every single time I solve a problem. But in the end, it's also if we introduce it as a shortcut and never explain it, that's why math is such a hated subject. Because it makes more sense when you expand on the idea. And then what do? We take the 20, add it to the 3. Well, that's just the basic addition of this, and that's 23 over 4. So, and then in the future, it gets weird because when we say, hey, when there's no sign between, like a plus or a minus between numbers, you call that multiplication. So some students will look at this and be like, oh, multiplying these two. No, incorrect. It's just because the instructions are so vague. Sometimes they kind of mix together, which is pretty annoying. So mixed fractions, they're really nothing more than just adding a whole number to a fraction. But this does raise the case that if I give you any values, now you know a shortcut. It's based on this little mixed value process. Instead of having to do I need to get top and bottom the same and all that jazz, just do it this way. Boom, multiply 80, boom, add 83. Done. I didn't have to do extra fractional adjustments and all that kind of stuff. I'm essentially throwing it out there. I'm a teacher between fifth grade up to college level. So whoever really needs it. I mean, if you don't like it, that's cool. But in the end, look, yes, it can be like elementary math. I get it. But the teachers ruin a lot of the processes and things that a lot of students miss. Like, math is cumulative. At this point, I assume, since you understand it's like, nah, I wouldn't call it third class. This is probably around fifth or sixth grade because I teach them. Um, but if you miss one thing from the past, it's going to haunt you in the future. That's just the reality of it. So I'm kind of going from beginning to end. I'm not really teaching anyone that's not interested, but anyone that may want to fill in some gaps. And these are from students that I've had. So, like, let me show you here. These are students I've had. So, in my personal opinion, these are the most common issues. So, I'm kind of focusing on the most common issues people miss in the past. And I've got plenty of students to go through, and I don't think I'm going to go through all of them now. But I'm not teaching any particular grade. I'm just kind of speed running the problems that I've seen through students. And I've been teaching for, depends on what timeline you're looking for. Overall, 15 years. I used to teach in Valencia College and University of Central Florida. So essentially, like, I can go to calculus if you really like to, but I'm pretty sure that's gonna be a little bit like, we may get there eventually with these sessions. Hi, Ziyad? Sorry, I'm horrible at this. Welcome in. Thanks for joining. If you have any requests, honestly, like throw them up here. I'd be happy just to like go over anything you guys may have currently be going through or have not gotten ever. I've had students that have been anything from 10 years old to 65. And this is for returning education too. In fact, I had a lady around 42 or 40 something, man, and she was struggling with fractions all her life, all her life. This was in Valencia College. We got to a certain point where we got her to understand fractions. She broke down and cried in front of me in the middle of the session where like all the students, not actually everyone was separated, like one computer lab, one over there. They'd raise a little flag, and whenever a new tutor would be available, we'd go to the flag that's raised. So raise your flags if you have any questions, ask them away. But this is how like strong this stuff is. This lady felt like this thing was like her demon, and she never went back to school because she felt like it would never work, like she would never get it. But that's completely from the truth. Um, it just takes a little bit of in-depth analysis on it. So that's really what these sessions serve for. I'm just going through content that I've had students go through and things that I find that are interesting to go over. There it is. There's some exponential pieces for you. Um, oh yeah, double square roots. What happens there, right? Well, you just have two fractions multiplying, which gives you the 1 over 4. So there's another case. Um, so yeah, I'm just going over some stuff. And if you'd like to join, it's totally cool. And if you want to ask some questions too, please do. I'd be happy to help with anything particular. Improper functions, rational, da 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 da. Mixed rate, da, da, da. Oh, decimals, yo. All right. Who hates decimals? Who? Okay, no. The question is, who hates decimals more than fractions? Because I think I like decimals, but I don't like decimals. I personally hate decimals more than fractions. Because again, this is going to be an opinion. And it really is a case of how much you feel comfortable with fractions versus just looking at a decimal. Because a decimal is always going to be just the 0 point something, something, something. But a fraction is going to have two numbers involved, the number in the top and the bottom, and how do they mix and how do they divide. So here's kind of a trick. Anytime you're dealing with a decimal, you want to convert it to a fraction. Let's go. 0.124. Okay. Doesn't matter what the number is. You want to convert any decimal to any fraction. You start with our instincts. We got invisible 1 underneath. The case that we're going to go for here is also bring up the invisible 1 after, because we need this to adjust the numbers. In our case, if you're not used to decimals and multiplying of tens, here's a great example for you. I'm going to change this 1 to a 10 over 10 because tens are great for decimals. They are absolutely mwah. What that does, there's two ways to look at it, right? The 10 will basically change this 0.124 and we multiply it. It's like 10 of itself, so we kind of think about it, it's the moving of a decimal. But in reality, if we have 2 times 10, we basically have a 20 involved. So if you really think about that 2 as a 2.0, why does it become 20? Because we're moving the decimal at the end and then putting it here and then removing this one. Can I remove that without destroying everything? Oh, nope. So moving that decimal is a form of multiplying of tens consistently. In this case, we will do the same thing. I mean, if you do it in the calculator, it's going to give you the value, but this is going to be 1.24 over 10. You got to keep that balance, right? But if you do that little instinct, you're going to have the balance automatically done. So that's great, but it doesn't really get that into a normal number. So then we count how many zeros we're going to need. 1, 2, 3. We want to move 3 decimal places. So let's put 1,000 over 1,000. Set that equal. That's going to give us a 124 over 1,000. Then I made this evens, so it's a little bit easier to kind of process. If you have even numbers and you're trying to simplify, divide by 2. That'd be 62. And the bottom will be 500. And then divide by 2 again. That'll be 31 and 250. Now, there's not evens anymore. This is kind of a trick with division, so that's a whole section to go over on how do you identify what divides nicely. But one of the main cases is that if it ends in an even number, then you can divide by a 2. Tens, zeros are normally even related, so you can always do that. There's again a 62, divide by 2. But then here we have a 1 not even and a 0. So bottom's even, top isn't, but we're kind of stuck here because 31 is technically, I'm pretty sure it's a prime. So there it is. This number, whatever this I pulled out of 0.124 is actually 31 over 250. So there's your conversion method. You're always able to essentially take any decimal, whatever it is, Heck, we can go to like 0.5, right? We should know this one, but hey, for practice. We know we need one decimal movement. Then, well, now in this case, we're dividing with something that they have both in common. The way I like to think of this is find some multiples. 5 is 5 times 1. 10 is 5 times 2. Change those into 5 times 1 and 5 times 2. Cancel them. And now you have a half. It kind of like reverse instinct here. We're forcing it to go to a 1 so we can make it go away. Because we know we can pull out a 1 anytime we want. Like this guy here. That's technically a 1. It's 10 over 10. Or we can reverse the process and find something in the division that makes a 1 and just get it out of the way. Or canceling top and bottom, which is also not technically true. You don't cancel the numbers on the top and the bottom. You're simplifying. So like it's when we get to variables we'll really get into the nitty-gritty on that detail. But just remember, you're not canceling the 5 over 5. Canceling means going to 0. Cool. 31 is prime. Thanks for that. So can do it with anything. So half off, you know, go to battle pass, you have half off. That's 1 over 2 off. How do you go from fractions to decimals? It's just not going to be nice, right? I don't like going that direction, but in reality, we're just completing a bus method. Anytime we have 1 over 2, we divide the 2 by the 1. We go through the process. 2 goes into 1 0 times. And that's a 0. Subtract a 0, still a 1. We need to complete the process, so we need a new 0 next to 1, but we got to throw in the decimal, which we throw at the top as well. Throw in the extra 0 in the decimal space that we can pull out another case of imaginary, but this is the more understood one. We know that there's a bunch of zeros after a decimal, if we decide to show it. We drop the 0 down. Now 2 goes into 10, 5. 5 times 2 is 10. Always subtract 0, and we're done. So typical process here for division, right? This is just division in its purity. But no one knows that you can take any decimal. No, no one knows, but it's not a common, what do you call it, process that we are familiar with and automatically go for. We don't take a decimal into fraction because we're like, oh, no, now I got to think of all the base decimals. Well, 1/2 is 0.5 and 1/04 is 0.25, and maybe you'll know 1 over 8 is 0.125. Yeah, 0.125. You take a 1 over 4 and divide it into, which is 0.25, divided by 2 is 0.125. You do this enough, you become a calculator in its own. But you don't need to know those decimals to be able to do the conversion. Just this little rule. So what's the shortcut? Well, take any decimal, 248, and put a 1 underneath, give it a decimal. You know you're going to go 1, 2, 3 times. You know you're going to go 1, 2, 3 times. So there it is. Shortcut, 248 over 1,000. And now you can basically simplify and go about your way figuring out what the simplified version of that fraction is. But notice that this division of 2 that I did here, which is basically 2 over 2, is the same thing I've done here with the 5, at least not the same thing, but it's the same math. We approached it 2 different ways, but still canceled out a 2. Over here, I made apparent that 5 times 1 is 5 and 5 times 2 is 10, but I didn't do that here with 124. I could have said 124, split it into 62 times 2 and 1,000. And then 1,000 is 500 times 2. And then if I didn't have all this extra stuff, then the 2's will cancel, which still gives us 62 over 500 for the next case. So strategies of different types, sure. But in the end, they help with specific cases. So when you're dividing by 2, it's probably much easier to divide by 2 than to have to separate a large number into smaller pieces. Oh, this makes me want to play some StarCraft, honestly. Whole numbers and all that jazz. There's me explaining to my student the process. Oh yeah, well, exponents. Once you kind of see it before, now you start to make sense of it. You have one, two, three, four, five, and six fours on the top based on the fact that a power of six is just a replicated copy and paste of the four six times. And then you have a two at the bottom, two fours from the square. If they're divided, well, there's your division. You apply our instincts. There's a one here and a one here. They go away. You're left with, oops, one sec. Undo. Okay. And you're left with four fours on the top, which makes four to the fourth power. So being able to see it from the instinctive perspective, you just take some stuff apart into their base components based on the math instincts we went over earlier, and you cancel out the things that are the same. Another way to look at it is through the format of exponential interactions. If you have a division in the middle, then you technically have subtraction based on the properties. But where did the properties come from? Well, they came from here. Just the basic concept of we're just canceling out top and bottom. So it's a -1 for every time they cancel. And that's it in the end. No, wait a minute. I don't want to go too far into this, but now we're going to exponential equations. Quadratics. Hmm. Let's see Juanita. She was one of my good students. She knows and went through a lot. Conversion? No, what's this? Word problems. Yeah, true. Word problems tend to get messy. I always say that math isn't the problem. Math is pretty easy, but when it comes to the English, it starts getting more difficult. I'm not gonna go over word problems today, but I might consider that a future session because they can just get tricky. That's all. Let's see. Long division, fine. Units. Let's see. I think I might call it for this session. How long we at now? 42 minutes. I really want to play some StarCraft. I'm probably gonna do some StarCraft. I'm gonna stream some StarCraft. So I'm gonna call it here. These videos will be recorded on YouTube, so if anyone ever wants to see them again, they'll be in the live space. I'll put them under academics too, or academia, the playlist I have for all of my essential learning streams. What is this bee doing here? So if you want to watch it again, go there. If not, it's cool too. But I'm gonna play some StarCraft and I'm gonna stream it in a